Hello, Calculus 2 students. This video, we will work 10 series from section 5.3. The direction is all the same. Determine whether each series converges or diverges, fully justify our response, and this includes stating any test used. 5.3 is non-negative series, and we had many tests, and so we will see a variety of tests used among these 10 series. Wonderful. Well, this first one is a short one. I can rewrite this using a positive exponent, but in the denominator. So this is 1 over n raised to the square root of 2 power. Now we see this is a p series. This is a p series, and p is the square root of 2. The important thing about p here is bigger than 1. The square root of 2 is bigger than 1. And so this series converges. Number 2, we have 3k divided by k plus 2 factorial. Well, terms are going to 0 here, so I cannot use the term test. But more than that, because of the factorial, my first thought is to use a ratio test. So let's do this. We take the absolute value, ak plus 1 over ak. Now here, this is non-negative series, so I don't really need the absolute values, but I write them just because I'm used to doing that with ratio test. Okay, evaluate at k plus 1. We have 3, k plus 1, and then we have divided by, this will be k plus 3 factorial over evaluate at k. We have 3k over k plus 2 factorial. Well, at this point, what I do when I'm using a ratio test, I invert, multiply, and line things up so that they match. So in particular, I'll write 3k plus 1 over 3k. And then this part, the k plus 2 factorial, I'll put on top of k plus 3 factorial. The nice thing about factorials is this will simplify more. So maybe I will come here. I'll do this in 2 steps. First of all, 3 over 3, that's 1. So I have k plus 1 over k. And then I have a k plus 2 factorial. In my denominator, k plus 3 factorial is k plus 3 times k plus 2 factorial. And here, this is 1. So I'm left with k plus 1 divided by k. I'll multiply this out. K squared plus 3k is fine. I could have written as k times k plus 3, but this is my simplified absolute value ak plus 1 over ak. Now we take a limit as k goes to infinity. This is a limit as k goes to infinity of this simplified. We have simplified it so we can actually calculate this limit. Now, what am I looking at here? In my numerator, what dominates is the k. The denominator, what dominates is the k squared. This limit is 0, which is certainly less than 1. And so we quote the test, ratio test, and state the conclusion. This series, k equals 2 to infinity of 3k divided by k plus 2 factorial converges. Number 3, when I see sine squared, well, first of all, this is a non-negative series, but more than that, sine squared is always less than or equal to 1. When I see this in a series, what jumps to mind is comparison test. But I can do more than just compare to 1 over this denominator because, well, ideally, I want to compare to either a p series or a geometric series. So let's take a little 2-step process here. First of all, this is non-negative, so sine squared n is less than or equal to 1. Now I can just put this denominator. The denominator is the square root of n cubed plus n. N cubed plus n. But here's the second step that I want to do, and this is where I'm going to set my comparison up. You notice what dominates here is this part for n very large. And bigger denominator means smaller fraction. So this is less than or equal to 1 over the square root of n cubed. Now, wonderful, let's justify. This series, the sum, n equals 1 to infinity of 1 over, well, we can write what this is. This is n to the 3 over 2. The square root of n cubed is n to the 3 over 2. You notice this is a p series where p is 3 over 2, bigger than 1, converges. Now I'm not finished because I need to quote the test that I've actually used. My actual series, the terms are less than or equal to a convergent p series, term by term. And so we quote the test. This is just direct comparison. By the comparison test, this unknown series, sum, n equals 1 to infinity of the sine squared of n divided by square root n cubed plus n converges. So far we have 3 convergent series. Well, I can tell you we will have a 4th in the next one, but it's definitely not the case every series converges, and we will see that in some of the coming series. So let's do the next one. Number 4. N over 4 to the 2n. These are the terms of this series. Well, we have many, many options here. In fact, for many series, there might be options that work equally as well as what I present in this video. I can name a few. You could use integral test on number 4. You will have to use integration by parts, but it will certainly work. You could do a ratio test. I think that's what I meant it to be when I wrote the question. You could also be clever and do a comparison, but let's do ratio test because that's what I was thinking when I wrote the question. So let's take an absolute value of an plus 1 over an. We have n plus 1, and then in the denominator, you see when you evaluate 4 to the 2n at n plus 1, we have 4 to the 2n plus 2. Now, divide, evaluating at n. Invert, multiply, and line things up that match. So we have n plus 1 over n. We have a 4 to the 2n over 4 to the 2n plus 2. Well, n plus 1 over n, we can't simplify. But this other one, you see, in the denominator, we really have a 4 squared, which is 16. Okay, this is as simple as we can make it. Now we take a limit as n goes to infinity of the absolute value an plus 1 over an. This is a limit as n goes to infinity. We have n plus 1 divided by 16n. Well, this limit we should be able to look at and know what's happening. We have n, we have 16n. This limit is 1 over 16, which is certainly less than 1. So, quote the test. We have ratio test. And then the conclusion. When this limit is less than 1, the series converges. Okay, let's move on to number 5. Number 5, number 6. It looks like a lot going on here, but both of these are quite similar. Both of these should be shouting to you, root test, root test, root test, because we see something all to the k in both 5 and 6, and this is perfect for the root test. So we'll do number 5 first. Here, we want the kth root of the absolute value of ak. Well, this is non-negative, but I still write it with the absolute value because that's the general statement. What is this here? Well, in my numerator, you notice I have a cube root of k raised to the 2k power. In the denominator, I have a k to the k. Now, the kth root, we are raising all of this to the 1 over k power. Like this. Okay, well, power to a power, we multiply it in both the numerator and the denominator. So my numerator becomes the cube root of k squared, which I can write as k to the 2/3. My denominator, power to a power, we multiply, we just get k. One more step. This is 1 divided by k to the 1/3. Now I can take a limit as k goes to infinity of the kth root, absolute value of ak. This is a limit as k goes to infinity of this 1 over k to the 1/3 power. Well, denominator is growing without bound, fixed numerator. This limit is 0, which is certainly less than 1. And so we quote the test, root test, the series, k equals 2 to infinity. Maybe I will just copy and paste the terms. Converges. Well, so far, we've had 5 convergent series in this video, but it's definitely not the case that every series converges. And we will see our first divergent series in this video here in number 6. So we see something to the k. Root test, root test, root test. Let's go. We take the kth root of the absolute value of ak. Now here everything is non-negative, so I don't really need the absolute values, but generally we would if we had a series with positive and negative terms. So you notice my terms are k cubed plus natural log k, and then we divide by 4 plus 1/2 k cubed to the k. That's the kth term. Now raise this to the 1 over k power. Power to a power, we multiply. We're left with just this, k cubed plus ln k divided by 4 plus 1/2 k cubed. This I can take a limit of confidently. So let's take a limit as k goes to infinity of the kth root of the absolute value of ak. This is a limit as k goes to infinity of this simplified. Here, k cubed dominates the numerator, 1/2 k cubed dominates the denominator, and we can see the limit. It's 1 divided by 1/2. Which you notice this is 2. This limit is bigger than 1. So we quote the test. Once again, this is root test. But this time, the limit is bigger than 1, and so my series diverges. This is the conclusion of the root test in this example. Number 7. First thing we might think about is what's happening to the terms. My numerator, I have an n squared. My denominator, I have an n cubed. N cubed is higher power than n squared. The terms are going to 0. Term test tells us nothing. Well, that thought process tells us what to do here because for n large, this looks like harmonic. So let's make this observation. This looks like the harmonic series, which is n equals, it starts at 5 to infinity of 1 over n. N squared over n cubed is 1 over n. This is harmonic, and it diverges. You can also justify this by saying this is a p-series with p equals 1, which is certainly less than or equal to 1, diverges. But we can also quote the harmonic series. Okay, so the options here are comparison or limit comparison, but direct comparison will run into a problem. To compare to a divergent series, we need to be term by term bigger. And here we have a smaller numerator, that's a smaller fraction. We also have a bigger denominator, that's a smaller fraction. So I need to use limit comparison here. Direct comparison, the inequality doesn't go the right way. So let's take a limit. As n goes to infinity, we take the nth term of one series, we divide it by the nth term of the other. If this limit is finite and positive, then both series have the same behavior. Well, this is a limit as n goes to infinity. We have n cubed minus 2n over, we have n cubed plus 4. Now we can actually evaluate this limit. We have n cubed, we have n cubed. This limit is 1, which is positive and finite. And so we quote the test. This one is limit comparison test. And it says that my series, n equals 5 to infinity, n squared minus 2 over n cubed plus 4. Well, it says it has the same behavior as the series I have justified, which is diverges. Number 8. We want to be careful here because this is definitely not k factorial over e to the k. It's not k factorial over e to the 2k. Neither of these. If this was the terms, this would be a totally different behavior, totally different series. This would be factorial over exponential. We could use growth rates and the term test. That is not this. We have e to the k squared in the denominator. So because I see factorials, ratio test. So let's do this here. We take an absolute value, ak plus 1 over ak. We have k plus 1 factorial. In my denominator, we have e raised to the quantity k plus 1 squared. And then here we have k factorial, and then over e to the k squared. Okay? Invert, multiply, line things up. So I have k plus 1 factorial divided by k factorial. Then I have an e to the k squared. Here's where I have to be careful. I'm going to go ahead and multiply this out. This is k plus 1 squared, which is not k squared plus 1 squared. There's a first, outer, inner, last, right? So in my denominator, I have an e raised to the k squared plus 2k plus 1. Now I can definitely simplify some things here. My numerator is just k plus 1. We have k plus 1 times k factorial over k factorial is 1. But you notice I have something in my denominator. I have an e to the 2k plus 1. Properties of exponents. Well, now I'm ready to take a limit as k goes to infinity of this ratio, absolute value ak plus 1 over ak. And I have simplified it. In fact, I've simplified it enough to where I can actually calculate this limit. Well, now is where we can use growth rates. This is a k dominating the numerator. My denominator, this is exponential. Now we have exponential. So without a doubt, denominator is growing significantly faster than the numerator. This limit is 0, which is less than 1. So we can quote the test. This is the ratio test. It gives that this series, k equals 0 to infinity of k factorial divided by e to the k squared converges. Maybe I'll make that a different color so that it stands out from the work. This is a convergent series, and we use the ratio test here. This was a fun problem. Last two, 9 and 10. If you look at these, you notice how similar they look, but they have different behavior. I'll tell you that in advance. And the tools I will use, or the series tests I will use, will be different for these two series. Okay, so let's do number 9 first. You might think you want to just jump in with a ratio test. I'm telling you now, will be inconclusive. You should try it. In fact, 9 and 10 both. The ratio test will be inconclusive. If you take absolute value, ak plus 1 over ak, then you take a limit, you will get 1. But with number 9, you see, what I see when I look at this is something that I can integrate, and I can't think of another tool that will be easily applied. Terms go to 0, can't use the term test. And comparison, limit comparison, those are a little bit problematic in my mind compared to just jumping in with an improper integral. So this takes a little bit of work, but for this series, this is what I would do is the integral test. Okay, f of x is 1 divided by x ln x. This is my continuous function. It is, well, it's continuous. certainly. It is non-negative, in fact, positive. And it is decreasing. It's decreasing because the denominator is growing and we have a fixed numerator on this 2 to infinity. This means I can use the integral test. If you use it, and you know, this is the first time we've used it the whole video. I use it only when I need to, so I don't use the integral test that much. But if you use it, you have to actually verify these hypotheses. It's part of the work. So let's calculate this improper integral. 2 to infinity of 1 over x ln x dx. This is substitution. U is the natural log. Du 1 over x dx. You notice I have exactly du in my integral. Now, personally, I change my bounds, but before I do that, let's write the definition. The limit as b goes to infinity, integral 2 to b. Okay, now I can change my bounds. Even if you are doing an improper integral as part of an integral test, it doesn't mean you can take shortcuts on the improper integral. The full improper integral needs to be part of your work. Okay, let's change my bounds. X ranges from 2 to b. U will range from ln 2 to ln b. So I have a limit. As b goes to infinity, I have the integral from ln 2 to ln b. And you notice it's 1 over u, du. We keep writing limit until we evaluate. So I am still in the definite integral part of this improper integral. Well, we have ln, absolute value of u, and then we evaluate between ln 2 and ln of b. This is natural log of b minus natural log of 2. But what's happening here? As b grows without bound, this part, ln b grows without bound. If you take ln of, well, inside the log is growing without bound. So this will grow without bound. So this is going to infinity, which says diverges the improper integral. Now, I need to go back and speak about this series, but I'm almost there. We quote the test. This was the integral test. And we state the conclusion. It's that the sum, k equals 2 to infinity of 1 over k ln k diverges. Then maybe I will do this part in gray so we can see a difference between the improper integral and series. Number 10. Well, I mentioned this one will have different behavior, and personally, I'm going to use a different test. So we have k squared, natural log of k squared. To me, that's not so straightforward to integrate as the one above, for example. But more than that, I tend to avoid the integral test if I can. And here I can, because if I didn't have this, natural log of k squared, well, what is this? This is a p series, and it converges. P equals 2, bigger than 1. So let's start writing that. Let's write this. We consider this p series 1 over k squared. We can justify this. This is a p series where p equals 2, bigger than 1, converges. These terms here, I multiply by ln of k squared. And let's see, as long as k is bigger than e, natural log of k is bigger than 1. And so you would have a bigger denominator. Bigger denominator means smaller fraction. So let's set up that inequality right now. Okay, it's going to be comparison. So we have 0 is less than or equal to the terms of my actual series is less than or equal to 1 over k squared. Now I need here, this would be for k bigger than or equal to 3. My series starts at 2. I have this inequality for k bigger than or equal to 3. It's fine. As we discussed in class, the first so many terms do not affect the convergence. So having this inequality, so sort of forevermore, and this infinite tail is what we need here for comparison. So this series I have justified converges term by term. This series is less than or equal to. The terms of this series will converge. So we quote the test, comparison test, and the conclusion, it's that the sum, k equals 2 to infinity of 1 over, let's see, maybe I will write it as it was presented, 1 over k ln k squared converges. This is our final conclusion here. And this was the last one on the 5.3 exercises. 10 series. It was so much fun. Thank you so much.